In timestamp-based protocols, a unique, fixed timestamp is assigned to each transaction at a startup time. This happens before the transaction starts execution. We denote this timestamp for transaction Ti with TS of Ti. To enforce a timestamp-based protocol, we use the timestamp assigned in the start time to make decisions during execution time. During execution time, we ensure that if action AI of transaction Ti conflicts with action AJ of transaction TJ, and we have the transaction timestamp of Ti set to a value less than transaction timestamp of TJ, then AI happens before AJ. If the schedule violates this ordering, the transaction needs to be aborted, rolled back, and restarted with a new timestamp value. For scheduling based on timestamps for concurrency control, we need a timestamp ordering protocol, or TSO, that ensures to define the relation among the expected values of timestamps. To implement this concurrency control scheme, in addition to transaction timestamps, every database object O also receives timestamps. Each database object receives a read and a write timestamp. We denote the read timestamp with RTS of O and the write timestamp of object O with WTS of O. The read timestamp shows the largest timestamp of all transactions that executed read successfully. The write timestamp also shows the largest timestamp among all transactions that executed write successfully. Now, how do we define the ordering? Let's start with reading an object O. Say, transaction T wants to read object O. What can happen? If timestamp of transaction is smaller than the write timestamp of the object, it means that the most recent write on the object would violate the timestamp between this transaction and the writer transaction. This will result in an overwritten object after read. Therefore, the transaction is aborted and restarted with a new, larger timestamp. If the timestamp of transaction is larger than or equal to the write timestamp of the object, transaction reads the object O, and the read timestamp of the object is set to the larger of the transaction timestamp and the read timestamp of the object. Now, let's discuss transaction's write operation. If transaction T wants to write object O, if the timestamp of the transaction is less than the read timestamp of the object, the write action conflicts with the most recent read action of the object O. This means that that value that it is producing was needed previously, and the system assumed that the value would never be produced. Therefore, the transaction is aborted and restarted. If the timestamp of transaction is less than the write timestamp of the object O, the transaction is trying to write an obsolete value. We can have different decisions here. But let's now proceed with the reject decision, and we will revisit the alternative later. So, the transaction resulting in an obsolete write is rejected. In other conditions than the two above, transaction T writes object O, and the write timestamp of the object is set to the timestamp of the transaction. As an example, let's consider transactions T1 and T2 in the figure. T1 is reading A and B to display them. T2 is transferring $50 from account B to account A, and then displays the contents of both. The read and write operations are highlighted. Prior to these transactions, the read and write timestamps of objects A and B are both 0. We said that a transaction is assigned a timestamp just at its startup time. We assume that the timestamp of T1 is 25 and timestamp of T2 is 26. The timestamps are only chosen to show the relevant earlier start time of T1. Now, let's discuss execution time. The read B will cause the object B have the read timestamp value of 25 after the first read on object B. Then read B from T2 happens, and since the transaction timestamp, which is 26, is larger than the current write timestamp, which is 0, it is allowed, and the read timestamp of object changes to 26. Then write B happens in T2. Since the write timestamp of object is currently 0 and the read timestamp of it is 26, the transaction is allowed and the write timestamp of object B is updated to 26. Then read A at T1 happens, setting A's read timestamp to 25. And this process continues at the execution time, and we can see that the transactions T1 and T2 meet the TSO conditions. And therefore, this schedule is valid. Now, how about this schedule? We can see that the write queue in T1 will have a conflict with the timestamp ordering using the second rule, because the write timestamp of the object is set to 26 at write queue in T2. And now, when the write in T1 arrives, the timestamp of the transaction is lower than the write timestamp of the object. In normal TSO, this transaction is rejected. However, a more permissive schedule can sometimes be applied using Thomas Wright rule. Thomas Wright rule changes the second rule of timestamp ordering protocol to ignoring the obsolete writes. Using this rule, schedule we saw in the last example will be accepted, ignoring the writes that will write the obsolete value. Applying Thomas Wright rule will allow accepting non-conflict serializable and non-recoverable schedules that were not allowed using the timestamp ordering protocol. So it is more permissive in the cost of giving up conflict serializability and recoverability.